Thank you. Quartz is the pricing and risk system of the markets businesses in Bank in America. And first of all, it is a platform, like any technology platform. If you want to start a new business-facing technology team in the bank, you just create a project in Quartz and you have everything available to you, from a distributed database, a compute grid, job scheduler, an SDLC system. We host your code. We manage your code reviews, your regression tests, your releases. You can start being productive immediately. So in that sense, it's like many other platforms. But as a risk platform, it has a particular purpose, and that is to be the repository of all the trading positions of all the businesses in the bank, so that the trades are stored in one place in a consistent format. Once you have something like this in a bank, it becomes possible to calculate risk in aggregate and treat the whole thing as if it is one big portfolio. And that, in the financial crash of 2008, became very clear how important it is for banks and financial institutes to be able to do that. Quartz started in 2010 as a reaction to that. That yellow circle at the bottom, that's where I work. I'm responsible for one of the core libraries of the platform. It's a dependency graph, computation graph management system that I will talk about briefly later. But the subject of this talk is actually, what is it like to look after a library that is a core library for such a large system? What are the maintenance challenges? How do we tackle those maintenance challenges? So first, let's see how big Quartz really is. I have all kinds of numbers here. We have compute grids with hundreds of thousands of cores. We book 8 million trades a day. We have petabytes of data, tens of thousands of batch jobs in Icon. These are kind of individual applications. I highlighted in red the stats about the size of the code base and the velocity of change in it, because that is kind of what relates to code maintenance, right? We have over 80 million lines of code. We have 4,000 developers making about 1 million commits per annum. That means a few thousand code changes every day. So we need to manage that. And the question I asked in the abstract is, how do I safely make changes in a library that all of those different tens of thousands of small applications are using without breaking them? Well, you might say this is a solved problem. What people usually do is the library has a version, and when you make a change, you bump the version number, and when a user wants to upgrade to the new version, it's their problem to change their code and make it work. So why am I here? Because in Quartz, we can't do that. In Quartz, the individual applications are the pricing and risk calculations of the different businesses. And we have this horizontal layer at the top that needs to aggregate all that. So these individual applications, they can't advance independently of each other. They have to play nicely together. They have to support the same APIs. They have to represent data in consistent ways. So I'm here in that yellow circle at the bottom. If I make a change, everything can be impacted. The whole system can be impacted. And it has to adjust to my change kind of simultaneously. That's the challenge in Quartz. And that is why it's an unusual maintenance challenge. So, you know, how do we go about doing this? Do we bundle a few thousand code changes every day and release that? Well, in a few thousand changes, some of them will be bad. The build would be broken all the time if we tried to do that. So we don't do that. We have a release management system that works kind of like this. It has versioning, but it's not the traditional versioning that we're used to in, you know, open source projects and the like. Imagine that we have only 3 projects, and each project is just one script, right? Now, in your mind, extrapolate that to 10,000s of scripts and thousands of projects, and then you'll see the complexity of what's going on. So we have the production source code, which is all the code as it was released, but we don't execute that code. What we execute is we execute the versions that are in an execution environment. Each project has its own execution environment. So here you see the production execution environment of each of the projects, and it is equal to the production source code just by chance. And now we have this situation where we want to release some changes, and the change in project 1 can't be released together with the change in project 2 because there's some problem between them. They're not compatible. The change in project 3 depends on the change in project 2, so it has to wait for that to be released. So what we do is each project creates a new execution environment. It takes a snapshot of production codebase, adds its own changes, and says, this is what I want to release. Okay, this is how I want to run my production applications on that version. And we run all the tests on it, and the first 2 projects, all the tests pass, there's no problem, right? And the third one, we see the problem, the clash between project 1 and project 2 and project 3. And then the owner of project 1 will click the button to release, and then 2 things happen. The first thing is that version of the script is now in prod source. It's now in production source. And the second thing is that the execution environment was updated. So this execution environment on which we tested and came to the conclusion that it's OK, we want to release it, that is now the execution environment of project 1. And then project 2, the owner says, OK, I want to release 2, so clicks the button and releases, and then project 2 has a new version. And now we have a clash in production. Our production source is bad. Something's broken there, but nobody notices it yet because it's not impacting anything that is actually running in production. Project 3, it couldn't release because we had test failures because of that clash that we had, so it rebases its execution environment, picks up everything from production source, overlays its own changes, and now it can't release because of the clash between project 1 and project 2. So that has to be resolved before project 3 can release. So what you see here is that we do have a versioning system, but it's different from what you're used to, and it keeps everything in production safe. So if we look at this versioning system, what it means for maintainers of core libraries, it's coarse versioning. Everything has to be picked up at once from production. All the code from other projects are picked up at once. You cannot cherry pick which libraries you want to upgrade and which you don't. And another thing is that you're not allowed to stay too far behind. So you have to rebase your execution environment within something like 2 or 3 months. Many teams have a 2-week system. Every 2 weeks, they will rebase automatically and release, whether they have changes to release or not. They will just update their execution environment so they are in sync with the rest of the universe. And what this means is that any change I make in the library that I'm responsible for is going to be felt everywhere within weeks, but not simultaneously, which is both good and bad. It's nice that I can't make a mistake and break everything on one day. It would be a very long day. But it does mean that I need to worry about backwards and forwards compatibility. Because if there's one application that produces data and another application consumes that data, I don't know which one of them will pick up my change first. And I need to make sure it works no matter what happens there. But on the upside, I don't have to worry about very old versions. So the backwards compatibility is 2 or 3 months back, which is nice. So it is what it is. That's our release system. That's how we need to work. And the most important implication is that it is my problem how my changes impact other people, because if I make a change that requires people to do some kind of complicated refactoring in their code, I can't just release that, because then they can't, I'm blocking them from releasing any other changes that they need to release. And that just doesn't fly. They won't respond well. So it is my problem how the code is being used and what I'm going to break when I release a change. Now, if we look at the particular library that I'm looking after, it's a dependency graph library. I'll just tell you briefly what it does. We call it the DAG. That's its name, for directed acyclic graph. And it's a graph of computations. And it's very a lot of banks end up with a system like this because this is what you get when you scale out of Excel. Pricing is basically what is the value of my portfolio, and risk is how does the value change when I perturb inputs, right? If interest rates change by 0.25%, what happens? If the Swiss franc moves by 30% in one day, as it did a few years ago, what happens? If Lehman Brothers goes bust again, what happens? And for that, for these two calculations, we have the DAG to model our calculations as a data flow. Think about Excel. You wouldn't be too far off. And the what-if scenarios we have features in the graph that are specifically designed to make them efficient. So it looks something like this. You write some Python code, and you annotate it. It looks like normal Python, but then you annotate it with some DAG stuff. And then instead of just calculating here, this example is a sum of squares calculator. Instead of just calculating the sum of the squares of the inputs, it will spawn a graph in memory with a node for every function invocation with the value of that function memoized. And it will also remember dependencies so that you can say, what if B is 2? And then it will invalidate whatever depends on B and recalculate that, but it won't need to invalidate the other branch which doesn't depend on B. And that's very important. Now, this decorator that turns this stuff into a DAG function, it does quite a lot of work, as you can imagine. There's a code translation stage involved here. That's something that Python is very good for. It lets us decorate functions. We can inspect them, look at the syntax tree, compile dynamic versions of the translated code. Python is very good for that. And this transformation, it intends to preserve the semantics of Python. By and large, it does, but occasionally things break down. And a lot of what I've been doing over the last 3-4 years was to kind of deal with that, to either make it work more like Python, because it's very confusing for people when they think they're writing Python and then it does something different. Or if it's impossible to make it work like Python, then just block certain patterns and say, this is not a safe pattern, I'm going to throw an exception instead of giving you some wrong result and let you debug it for a couple of weeks before you realize what happened. So it's that kind of work, and also bugs. Just, there were some bugs that needed fixing. And so this is an example. This is a simple example. We had an exception handling method. It was called suppress errors, and it did pretty much what it sounds like. If there was an exception, the exception was swallowed and stored somewhere, and you got an error value, and you could go and figure out what happened. It was very confusing for people because it's so different from the way Python works. And you can see that the number of instances, the top line, it flatlined, right? Nobody was using it anymore. It was flat. It was kind of flat for a few years back. It was just, you can't handle exceptions on the graph, don't even try. And then one of our users had an idea how to make something that works like Python. And I worked with him from July 2017 to implement it, test it, release it. And you can see that we had a few instances in the code base. This is like we're testing it. It's a long testing period, but exception handling is a sensitive feature. If you get it wrong, it can be very hard to debug. So I was careful. So if we tested, we found a bug, we fixed it, found another bug, fixed it, and then I was up for promotion. It was a bad time to destabilize the bank. So I waited a bit more, and then it looked fine, and we released it, and people started using it, got excited, and at some point, kind of earlier this year, we decided, that's it, let's get rid of the old one. We don't need it, it's no good. And we drove it down. It's almost 0. Not quite, because one project said we're going to decommission this application at the end of the year, leave us alone, so I left them alone. So it's almost, we almost got rid of this feature. This plot, I mean, I'm just showing it as a simple example of how we replaced one feature by another, but if you think about how did I produce it? So it kind of shows you what we can do in Quartz. We host everybody's code. We can scan everybody's code. We can scan everybody's code as of some date in the past, and we can distribute that job to the grid. So I can get a plot like this for the whole code base from 2010 until now in about 20 minutes, which is fun. It's better than working. And the second example I wanted to talk about is we had a feature called layer in the graph. Layers are a very important feature for what-if scenarios. They allow you to do a what-if scenario without destroying the original graph. So you kind of do this. This is the scenario we did before when B was actually 2. So we do it on the side in a copy and write kind of way. So it's that graph, but with this change. So this is a very important feature. And we had a bug in it. It was a bad bug, a really, really bad bug, like as bad as a bug can get. It showed up in weird ways. Anything that happened could have been because of this bug. And it caused a lot of problems, and when we tried to fix it, it destabilized too much stuff. And in this case, we didn't want to rename the feature, both because it's a very common feature. It would be the cognitive load for our developers would be too high, and also because the bug only impacted a small minority of the instances. So about 800 out of just under 10,000 instances, and it depended on the context in which you used the layer. So what we did is we versioned the feature. We added layer 2 and said we're going to fix this bug and a few other bugs, minor bugs, and ask people to can you just give them a list of all these 800 places where they're vulnerable to the problems. Can you just migrate, test, release, do it by the end of the year or end of next year? And we started in September 2016. We said, end of 2017, we're going to flip layer to become layer 2. So by then, that's enough time. And then we change layer 2 back to layer. That's after we flip, because they are the same thing now. And then we can forget any of this ever happened. So that's a good plan. Takes 3 years, but it's a good plan. But you see that layer never went to 0, right? So why was it OK to flip then? Why didn't it go to 0? Probably a lot of it is dead code, but how do I know? Maybe they tried, and they had a problem, so they stayed with a broken feature. So what we did is, at some point, we realized we're going to have this problem. We can't kind of make sense of what's happening. So we added the broken feature as an option. If you really want to, then you can use layer as it is today. We called it layer with bugs because we like to be clear. And people moved. You can see that some people actually said, we don't want to change anything. We're happy with the way things are. Right or wrong, these are the numbers we want to give out. And they are using, still, a few people are using layer with bugs. We're kind of pushing to get rid of it. But the point is, this is kind of OK, because nobody's going to use layer with bugs by mistake, right? We're not going to see that in new code that people write. So we haven't eradicated the bug, but we have contained it. And this curve here, this is, I refer to this as my learning curve, because that taught me that inertia is very strong. And you can't get rid of anything, no matter how awful. And now when we add things that we want to block, when we want to raise an exception when you use something that is unsafe, we added something called an unsupported mode. And what unsupported mode does is it has all kinds of options, and you can say, let me do this bad thing. And then you do that bad thing, and then instead of an exception, you get a warning in the log. And that saves a lot of time, because I don't have to debug the same problems again and again, and they report bugs, and I say, no, it's not a bug. On page 19 of the manual, we told you not to do this. We don't have this dance anymore, and it's not something people are going to do by accident in new code. It's ugly syntax. It's obvious that something bad's going on here. You get the warning in the log. There is a governance report, so there's a report that managers can click on and open and see who's using unsupported mode. And this became our technical debt registry. People actually refer to this as, okay, we'll talk to our managers, we'll allocate time, we'll deal with it when it's the right time to deal with it. And this is working very well. We've managed to tighten up the APIs and make the whole thing more robust without breaking too much stuff for people. So to summarize, Quartz is a risk platform, which means that it's not a normal platform where you can just use traditional versioning to make changes in core libraries. All the pricing libraries, all the risk libraries need to be in sync with each other. So we have to be a bit creative about how we release changes, and we're figuring it out as we go along. Thank you.